Hey everyone, so we left off where we came up with some equations for the energy of a Fermi gas, as well as things like talking about the Fermi temperature and all that stuff. So we're going to take that one step further. Since we have a description of energy, we can come up with something called the heat capacity. Well, I shouldn't say something called heat. We come up with heat capacity. Now, as we know, when we're originally in the classical regime, when we're dealing with monatomic gases, um, the heat capacity is on the order of 3 halves n. Now, the thing though is that something like this doesn't actually always work in what we would consider the classical regime. So, for example, as you may know, surrounding metals have a very loose grasp on their electrons. So, electrons tend to be floating around in a uh, what could be seen as almost a sea or a cloud of electrons. This is actually one of the reasons why metals are really good electrical conductors, is because of their loose grasp on the electrons, this free flowing electron around the metals. Uh, it turns out that these electrons can actually be thought of and worked on as considering them as degenerate quantum Fermi gases. So that's kind of one of the benefits to doing this, is that even though we don't normally experience fermions and bosons until they get close to that quantum realm, it turns out that there are some scenarios where they will end up where certain atoms and uh, particles will actually end up acting similar to what we would normally expect of, like with these degenerate Fermi gases. So we're going to consider a case where n number of electrons are heated from 0 to tau. So the total energy is going to be given by this: the energy at the base and then energy to some temperature. Now what we can do, because these two integrals both start at 0, this will eventually end up going towards the Fermi energy. We can actually split this integral into two, going from 0 to the Fermi temperature and the Fermi temperature to infinity, and then combining the one that goes from 0 to the Fermi temperature to this integral. And it would end up looking like this. All right, so we have this integral, which goes from the Fermi temperature to infinity, and this going from 0 to the Fermi temperature. All right. Now, the heat capacity is the partial derivative of the energy. So what we can do is take the partial derivative of this. Now, what we'd end up getting is this. Um, we can actually focus mainly on this aspect at the moment. Actually, we can actually recombine these together to go from 0 to infinity altogether, since now they'll be in like terms. And since we're considering metals, we're assuming that the temperature is going to be much less than this Fermi energy. And that would mean that this is large only when we're close to this Fermi temperature. So this equation can actually end up changing to look something like this. All right, so since we're using this degenerate Fermi situation, the distribution function that we're going to use is going to be given from what we got in the previous videos. So taking the partial derivative of this with respect to tau will end up getting us this complete mess. We can move things around, try to clean it up a bit, do an X substitution so it kind of makes it a little bit easier to work with. And then we can plug it back into our equation so that we can finally take an integral. taking the integral of this will end up getting us this pi squared over 3. So we end up getting that the specific heat for the electron gas around these metals is represented by this. Now the thing is, we actually do have an equation for this density. So our gas heat capacity can be rewritten in these two terms, whether we want to use tau or standard T. Now, because a lot of these terms are actually constants, with the only real one being this tau, the temperature that's going to be changing, we can actually substitute in this new term of gamma to represent all these constant terms. So it'll end up boiling down so that the specific heat is equal to gamma tau, where gamma is given as these terminologies. So for the most part, the gamma is supposed to be considered a constant term for the scenario that we're looking at. With a given number of particles and the known Fermi temperature based off of the material itself, the only thing that will actually end up changing would be the temperature. So this just kind of resays the same thing, that a lot of the electrons for metals in the valence shells, they're loosely held and surround the atoms, which is actually what causes the electrical conductions. So this was the equation we had for the Fermi energy. We can actually use this to end up finding out what the velocity of the electrons are at what they sometimes call the Fermi surface, which is just essentially that area between the energy level where everything above it is unoccupied and everything below it is occupied when we're at absolute zero. So if we set this Fermi energy to the kinetic energy, we can get something. Let me go back because I guess I don't resolve this, but you can end up rewriting this in terms of what we would call the Fermi velocity. Another thing that I wanted to mention, so we actually did talk about the specific heat of materials like metals, for example. In I think it was in chapter 4. We talked about the specific heat caused by photons and phonons, the mechanical and physical waves, and we should have gotten this relationship, A tau cubed. So we can actually combine these two into a more full concept specific heat that is coming from not only the free flowing electrons, but also the mechanical waves flowing through the metal. So one way that we can actually find the values of gamma, and this is actually one reason why this is useful, is if we can rewrite this equation so that we're solved by dividing all the terms by tau, and we'd end up getting a linear relationship that relates the specific heat divided by tau and tau squared. And what we'd end up finding is that the y-intercept gives us this gamma term. So this is actually one way that we can find these values. Because I know one thing that a lot of people are always wondering is how are we figuring out things like the number of electrons or the number or the Fermi temperature. How do we actually determine that? And this is kind of one of the ways that we can do it from our perspective by making measurements of the specific heat as a function of the temperature, as well as knowing what actually we wouldn't really need to even know what this A term is, but then graphing it and then seeing where it crosses the y-intercept, and then using that to figure out the equation, using our equation for gamma to figure out things like number of particles slash um, the Fermi temperature. All right, so here is the question. Pause video, work on the stuff, and we'll go over in a second. All right, so they want us to basically show that this is true, where this is representing the average number of fermions in each orbital. So we've done this before. The first step that we want to do is pretty much try to expand this section. So we can expand this into these two terms. So delta n, as we know, is going to be defined as n minus the average. The whole thing is being squared, so the squares is on the outside. And we're taking the average of this. So when we do this, it's going to end up boiling down to look like this. This is pretty much like an RMS almost. So the number of fermions can either be 0 or 1. So that means n is also going to be equal to n squared. What we can say is because of this definition, the average number of particles is going to be the same as the average squared of the number of particles. So when we have our term that looks like this, I can actually replace this average n squared with just average n. So from here, I could pull out an average n from both sides, or from both terms, and it will end up looking like this, exactly what they wanted. So a lot of this really boils down to this main step of recognizing that because fermions can either be 0 or 1, then this has to be true, which means this has to be true. All right. One last thing to mention about white dwarfs. So we had done a few questions about this, and I kind of mentioned it before. But for those who don't know, white dwarfs are essentially what occurs when stars that are pretty much around the size of our sun reach the end of their life. They're they're not able to maintain the production of fusion, so they end up compressing themselves into a much more dense star, and that's the white dwarf. So here I had mentioned before that an average star like our sun typically has a density of around just 1 grams per centimeters cubed, while a white dwarf can range anywhere between 10 to the fourth to 10 to the seventh. So, significantly more dense than our sun. Um, so this is actually one of the reasons why with white dwarfs, with their extremely high densities, will end up having or will end up being considered a degenerate quantum gas of electrons, despite not technically being at a low temperature state. All right, so we're gonna stop talking about fermions for a bit, and we're gonna go and switch over to bosons. So boson gases and the Einstein condensations. So, um, as I had mentioned before, when boson gases end up going towards their absolute zero, what ends up happening is all the electrons end up occupying the ground level. So there's actually a transition point where it goes from having just some particles kind of in that ground level to having a majority or a large percentage of them in that ground level. And once they actually pass this specific temperature point, they'll end up exhibiting very unique properties. Now, that temperature point that leads into this transition is usually called the lambda point. Um, and when occurs, the material is usually called an Einstein condensation. I mentioned this before that with senior lab course at Stony Brook, they have a situation where you get to work with superfluid helium in order to test some properties like its magnetic properties, and things like that, or heat flow transitions. And one of them is with liquid helium, the lambda point ends up being around 2.18 Kelvin. So a lot of times we don't normally get this this superfluid material or this Einstein condensation effect unless we get very close to absolute zero. All right. So here, what we're going to say is that we're going to consider a case where we have a gas with a ton of particles that is near absolute zero. So the ground energy level we're going to say is equal to zero. So if you recall, this was the energy that we had, or sorry, this was the occupancy function that we had for a boson gas that was degenerate or in the quantum realm. So if we set this equal to the ground level to figure out how many electrons are at the ground state, the equation will actually boil down to this. The energy part will end up dropping out. Now, we know that as the temperature ends up reaching zero, this should start going to n. Basically, the limit of this as t goes to zero, it should be equal to n. So the limit equation should look something like this. Now we can estimate or approximate the limit of this term to look something like this. Again, these higher parts can be dropped out because after a while it'll end up being practically nothing. So this will actually end up boiling down to look something like this, negative tau over mu. So in the end, what we end up getting is that when we start getting a boson gas uh, nearing absolute zero, then the chemical potential will end up being equal to this, negative tau over n. So this was, if we want to look at an example with actual numbers, what we end up finding is that if we have something that is essentially about a mole of gas at 1 Kelvin, then the chemical potential will be given by this number, 1.4 times 10 to the negative 31 joules. Now, if we go back to our definition of a lambda, because if you remember, we had used this new term to kind of simplify a lot of our equations to deal with something that we would call the activity, uh, which replaced e to the mu over tau. So if we use this, knowing that mu is essentially negative tau over n, plugging this in, and then using a pretty standard, I guess, approximation, we'd end up getting that the lambda term, the activity, is approximately equal to 1 minus 1 over n. All right, so here's the next question. You can pause the video, work on yourself, and I'll go over in a second. All right, so we're going to use this equation. And what they want us to do is first they said they want the lowest orbital level, which is just all ones. So that's what we'll do. We'll plug in a 1 into each of these terms. Because remember, these are our variable terms. So these three numbers are relating to these dimensions. So plugging in the lowest numbers, we end up getting that the energy looks like this. And then for the second energy level, where nx is just 2, the equation looks like this. So essentially, it just goes from 3 yada yada to 6 yada yada. Taking the difference of these will just be 3, or equal to this term up here, which will end up being equal to this. All right. Here's the next question. Pause the video, work on this stuff, and we'll go over in a second. All right. So now we're kind of using a lot of the same stuff from before, except now the temperature should be at 1 millikelvin. So in the first part where they want the probability of the particle being in the ground state, remember the way we do probability is by essentially taking this Boltzmann factor, if you will. So we can do that, and we know what the difference in the energy level is between the um, the first excited to the ground state. We got that from before, so when we plug the numbers in, we end up getting that it's approximately equal to 1. So yeah, we end up getting a fairly high probability of the particles being in the ground state since we're so close to absolute zero. So to find the chemical potential, we use our equation that we got before with it being equal to tau over n, and we get the chemical potential equals this. The next part, part C, they want the occupancy of the first excited orbital. So just use the occupancy equation into here. Now, if we could technically put in both the change in the energy difference, and the chemical potential, but it actually turns out that the difference in the energy is much greater than this chemical potential. So we can actually simplify it to just be equal to this. But honestly, it doesn't really matter. But what you should end up getting is that the number of particles within that first excited orbital would be equal to this. So, of the 10 to the 22 particles, we actually don't have that many. So, this may look like a lot, but as we'll see in part D, when we find the fraction of the particles, we find that that fraction is significantly small. All right, so moving on, we have this orbital occupancy and temperature. So, so we can actually take our definition for, since we're talking about near absolute zero and not exactly at absolute zero, we'll end up having a lot of particles in the ground state, but not all of them will be. Some of them will end up being in the excited state. So what we can do is we can come up with a definition of these two numbers. N0 is going to represent the number of particles within the ground state or the condensed phase, while Ne is going to represent all the particles in the excited phase, or sometimes called the normal phase. So we can use the density to figure out the number of particles. So the number of particles, as we know, is just going to come from adding the sum of the occupancies, which is just going to be the number of particles in the ground state plus the number of particles in the excited state. Or this term can actually be represented by this. So we can actually pretty much very quickly and very easily determine what n0 is without doing an integral, because we can just take the Bose-Einstein um, occupancy distribution equation and just set the energy equal to zero. Now, we can't do that for the higher levels because we don't know which other level the particles are in. They could be in the first level, the second, third, all the way up to literally infinity. So that's why we have to have that second part keeping and staying as a integration, while this can actually be very simply found by using this occupancy distribution equation. So Ne is done by solving the integral. So when we plug the numbers in for all the terms that we have, cleaning some stuff up, doing an x substitution to make our lives easy. We have to make the statement that because the number of particles is going to be very, very large, since we're so close to the ground state, to absolute zero, then this lambda term is going to be pretty much close to 1. So this is going to make our lives a little bit on the easier side. So our function for the number of particles in the excited state will look something like this. This integral can be easily found online. It's a pretty standard integration. So cleaning this up a bit and substituting in things like NQ, we end up getting this, that the fraction of electrons within that excited state is going to be equal to this relationship. The pretty much related to the number of particles in the quantum, the concentration in the quantum realm divided by the actual concentration. Now we can actually kind of rewrite this a bit, as we'll see later on. We can define something called the Einstein condensation temperature, which will be something where it's the temperature where all the atoms are in the excited state. Or another way of saying that, Ne ends up equaling N. So it's kind of similar to the Fermi temperature, where you can almost, it's almost like the opposite, I guess, where this is kind of saying all the temperatures to keep it from being in the all at the ground state, while the Fermi temperature was more of the temperature needed to keep everything kind of organized in the proper way. So the Einstein temperature will end up looking something like this, which means that I can rewrite the fraction of electrons to look something like this. So now it's going to be related to something more towards the temperature. Again, something that we can actually very easily and consistently measure rather than the concentration, which is a little bit on the tougher side. Now, if we take these numbers and we use the values for helium gas, we end up finding that the Einstein temperature ends up being about 3 Kelvin, which, as we can see, is very close to what we would experimentally find it to be about 2.17 or 2.18. All right, so here's a practice question. You could pause the video, work on this and we'll go over in a second. All right, so here we want to figure out this. So we want to find this critical temperature where Ne is going to be less than N. So Ne is given by this function, which can be rewritten so that it's solving for tau. Of course, we can actually get rid of it because they want the number in Kelvin. So they wanted a standard temperature, not absolute. All right. And then we just plug in the numbers. Here, because they actually give us the concentration, we're just going to combine the N and V into a concentration term. But for the most part, plug everything in. And we get that this critical temperature is 1.7 times 10 to the 6 Kelvin. So anything below this will make all the number of electrons in the excited states less than N. All right, here's the next question. Pause the video, work on this up, and we'll go over in a second. All right, so here they want us to find the heat capacity and the entropy, and they want us to use this and to keep our answers in terms of N and tau E. So starting off, we just want to kind of bring this statement up because we're going to need to have an equation relating Ne and tau, essentially. So that's what we're going to do. We're going to take this, rewrite it so it's in terms of the number of electrons, or sorry, the number of electrons in the excited state. So then we can plug this into the given energy equation that they had up here. And that simplifies to look like this. Now, specific heat is taking the partial derivative of this with respect to tau. So taking the partial derivative with respect to tau to the 5 halves gives us 5 halves times tau to 3 halves, which when we go back and again clean some things up, take some things out, we'll end up looking something like this. All right, so for part B, they want to find the entropy. So the entropy is done pretty much in a very similar way. Since we know what the specific heat is, we can actually relate that to another definition for specific heat relating to entropy. So we have this relationship. This can actually cross out one of the taus, and now we can integrate with respect to tau. So integrating this with respect to tau gives us a 2/3, and then it'll kind of simplify to look like something like this. So in the end, both of these part A and part B actually do have very similar forms, if you will. Right, here's the next question. Pause video working itself, and we'll go over it in a second. All right, so this is very similar to what we did in the last one. Unfortunately, I don't think it's going to be as simple as what we did last time because remember, unlike the fermions that can only be 0 or 1, here, not the same case. So we're going to pretty much use the same setup that they give us. So just like before, we want to try to work with this and see how far we could go with expanding this a bit. So according to this, it says that this left-hand term can be rewritten to look something like this. Now they also say that the average is equal to this occupancy with these terms. So we just take the partial derivative with respect to the chemical potential of that occupancy equation. We could plug in x's just to make our lives a little bit easier. And it'll end up looking something like this. So from here, we can then take this and clean this up a bit. And we end up getting this. All right. Here's the next question. Pause video, work on this up, and we'll go over in a second. All right. So what we're going to do here, we're going to start off with that occupancy equation that we have. And they say here that the lowest orbital is twice the population of the orbital at E. So we know that 2/3 of the particles are going to be at the lowest at the ground state, and 1/3 is going to be at the excited state. So the occupancy equations will look like these two, respectively. So working this around and solving it basically for this, we end up getting these two equations. If we actually divide both of these terms by each other, it will get rid of the mu over tau terms, leaving us with just e to the epsilon over tau, which simplifies to look something like this. So once we have this term, we can then take the ln of both sides to get rid of that e function, and now we could just solve for what they want, tau. All right. All right. There shouldn't be that much more to this, so I'm just going to try to finish up real quick. So superfluid of helium. Now, one of the things that we had mentioned before is that once the gas ends up crossing that lambda point and it goes into this degenerate state, this superfluid state, if you will, it gets these unique properties. A lot of those unique properties is actually more of a lack of properties, which is pretty much the interesting part. For example, with superfluid helium, it loses a lot of the properties that we would normally give with liquids, as it stops becoming a liquid, and it also kind of almost doesn't look like a gas anymore. Um, when you see a helium actually cross that boundary level, you'll actually notice that the line that separates, almost like the horizon that separates the liquid state with the fluid state, just kind of disappears, and it just kind of merges with the gaseous part. Some other things that it loses is it loses its viscosity, which is also kind of a useful thing. So here, now, if an object actually ends up traveling within a superfluid, the thing that we'd have to make sure is we'd have to make sure that it's not traveling fast enough that it will start to actually interact with the molecules and almost knock it out of this superfluid state. Because the reason why it's acting with zero viscosity is mainly because of the fact that no more collisions are occurring. Uh, so we want to try and limit how fast objects can move within a superfluid to kind of, as they say here, limit how many atoms end up becoming excited. So the critical velocity is given by this, taking the minimum of this term right here. Uh, and then here we end up having k, which is defined as the wave number. So just note this lambda is not the same as the activation lambda that we did before. It's completely different. So when we are talking about free atoms, this e to the k, the excitation energy, is given by this. So the critical velocity, when we take the minimum of this term, will actually end up being essentially equal to 0. When we're talking about phonons, e to the k will be given like this, where this is vs is the speed of sound, or a lot of times speed of whatever the wave is. We end up getting this. So the minimum will actually end up being equal to whatever the speed of the physical wave is. And that's pretty much it. Yeah, not really going to go over into that much detail with the superfluid helium. If you want to know more, you can look in the textbook for that, but I don't think the textbook even goes into that much more detail. So these were a bunch of the things that we talked about with the fermions and boson gases. We came up with a bunch of equations, a lot of them pretty much similar between the two. And then these are the homework questions for chapter 7. So if you have any questions, please let me know. Otherwise, I'll see you later.